Thank you very much. Just to clear it up to start with, can everybody hear me? The mic's working fine? Great. So first of all, thank you very much to the organizers for inviting me and giving me the opportunity to carry on doing some of the work I was doing during my research days. So I'm going to talk to you today again about least squares regression Monte Carlo, and specifically in the context of a subject that we've seen a few times already, this conference, backward stochastic differential equations, and also as a consequence how we can use this method for a class of partial differential equations of semilinear type. So just to introduce our continuous time setting, these are the problems that we're typically looking at. This is a forwards-backwards stochastic differential equation. So we've seen this already several times in the conference. It consists of a system of stochastic differential equations, one forwards in time, meaning that the value of x is specified at time 0, and usually there are d such equations, and then a second equation, which is the backwards type equation, where, as we see, actually the value of the equation, the value of y is specified at its terminal time. There is some effect between today and the terminal time capital T, which is nonlinear and captured by this function f called the driver. And then just to make sure that y is predictable, we have to include a stochastic term in a further process z, which subtracts, well, as we can see, all of this here is not adapted at time little t. It's actually taking in information from time little t to time capital T. So we have to subtract that extra information with this extra stochastic term to make y a predictable process again. So that leads to 3 terms that we have to solve for: an x, our usual SDE, which is d-dimensional, a y, which is 1-dimensional, and a z, which has the same dimension as the Brownian motion noise. Okay? And this is a decoupled forward-backward stochastic differential equation. As we see, y depends and z depend on x, but x doesn't depend on y. So how is this related to PDEs? Again, we've seen this a few times already, but just to quickly recall and to put it into my setting, Pardoux and Peng showed in one of their first papers on this topic that, in fact, you can express the solutions of y and z as deterministic processes of time and x. And those deterministic functions, are related to the solution of a parabolic partial differential equation, which is nonlinear in its solution and in its first derivative. And this is a semilinear parabolic partial differential equation. Okay? Semilinear because we have no nonlinearity in the differential operator in the Hessian terms. Okay? And this relation is actually very important for numerical schemes. Okay? I'm going to spend a lot of time, maybe half of this talk, building up towards the numerical scheme, and I'm going to build up from the continuous time processes that we've just seen, just so that it's very clear where the setup is coming from when we actually get to the least squares regression part. So, what are we actually going to do in the numerical scheme? Well, we have several goals. Firstly, we want to approximate the process x. Okay, this is actually not going to be the main topic of this talk. This has a wide amount of literature on it. It's not coupled to the other processes y and z. So we're just going to drop that notation from hereafter. So we're not going to be approximating the x, but in the full system you usually would have to. And we will approximate the functions y and z in a way that we try to minimize a loss function over functions in time and space, which take in, which is described by this norm. And this norm is the natural norm for which one proves the existence of backward stochastic differential equations. Okay? So it's an L2 norm, both in space and probability measure. And the final thing which is important is to tune the algorithm that we develop for approximating y and z to minimize computational costs and to actually make it tractable. So what we have is we have an objective that we want to minimize, but this objective is not actually tractable at the minute. Why? Because this function I've just shown you, it's all well and good to talk about it theoretically, but as a practitioner, the problem we see here is, well, our objective includes the solution that we actually want to reproduce. Okay? So what I'm going to do is I'm going to rewrite this loss function several ways until I've got it into a form that is fully tractable and usable for numerical algorithms. So the first stage of the approximation is actually to impose a time discretization. So one of the terms that was bothersome in the previous equation is actually this soup which appears in the expectation here. So this is very difficult to implement. So actually what I'm going to do is I'm going to introduce a finite and deterministic time grid, and then I'm only going to measure the error in y on points in that time grid, and I'm going to compute the maximum expected error along that time grid. And for the z part of the problem, I'm just going to measure the error, the square error in intervals that's in the time intervals that occur in the between each point of the time grid. Now, actually, people who are watching will notice, well, this is just a linear, the expectation is linear, so there's no difference to this and the previous equation, but we will discretize further in just a second, so don't worry. That's going to be, there's a reason I'm writing this like this. So L pi is going to be an approximation of L. L was our loss function. And obviously how we choose the time grid is going to affect how accurate that approximation is, as is the smoothness of the functions phi, f, b, and sigma that we use to define our equations. So there will be some material on the actual precise convergence rates of our numerical scheme that do capture this smoothness and the time grid, and those are going to appear as this talk goes on. Okay, I'm going to go here because it's easier than twisting backwards and watching. So, when we go to the previous slide, let's first of all just focus on the y terms. If we look at the original BSDE, okay, we see here actually to compute y, what we can do is just take conditional expectation, condition at time little t. The z term will just disappear, and what we're left with is just the expectation of the final value of y and the Lebesgue integral part. Okay? So we all know from our probability courses, our first probability courses, that actually the conditional expectation can be expressed as the random variable that is adapted to the sigma algebra ft, such that you minimize the expected square error between the random variable and the thing that you're projecting by conditional expectation. Okay? So we've written y as a minimization problem. In fact, what we can do, we can simplify our life slightly. So rather than taking this quite abstract space of square integrable functions, we use the Markov property to replace the square integrable adapted random variables to just random variables which are functions of x little t. And that's okay. So now we're left with y being this discretization problem. Sorry, this minimization problem. Okay, so how can we use this to improve our loss function? If I write the, so if I just take any function, deterministic function psi, and subtract the thing that I was projecting with the conditional expectation on the last slide, well, I can immediately use the fact that the conditional expectation is a projection to apply Pythagoras' theorem. So what I've done is I've just added and subtracted the y term, that's the solution, and I've split this sum, this square difference, into the difference between psi and y. So psi is the approximation I want to use, y is the true solution, and y and the thing that I'm projecting by conditional expectation. Now this was actually the thing I wanted to minimize in my loss function. This term here doesn't depend on psi at all. So in fact, to minimize this problem is exactly equivalent as minimizing this. So what I can do now is I can replace, in the y part of my loss function, I can replace this non-tractable term, because I didn't have this y, with a term here. This is the psi, this is the function that I'm approximating with. And then all of these terms only depend on solutions for functions for y and z that occur after time little t. Okay? And the whole reason why this is more tractable than what we had before is, of course, we know what y is at time capital T. It's just phi of x. So what we're going to do in the future steps that are coming is we're just going to work backwards in time, starting from time capital T, to evaluate y and z at all the earlier time points and thereby form this integral. Okay. So the optimal z also has an expression in terms of a conditional expectation. So if you remember, in the loss function, we were trying to basically find phi, which minimizes this, expectation of this integral. And now we're actually looking for a function, phi, that is fixed at time ti, so the first point in the time grid. Okay? But in fact, this is also a, this can also, the solution of this minimization problem can also be expressed as a conditional expectation. Now, this here, this is the measure with respect to the probability and the Lebesgue measure. So this is just the, this is a minimization, a square minimization problem, which you can write explicitly as the integral in time, just the Lebesgue integral of the process z, taken at the conditional expectation at the point ti. Okay? So this is a projection with respect to the measure of of probability and Lebesgue, okay, in O2. And if we just quickly go back, how are we going to, we can actually express this again in terms of these, that should be a plus there, sorry. We can actually express this again as a conditional expectation, not of integrals of z, but of these driver functions and terminal condition, by simply multiplying by the increment of the Brownian motion in the period ti to ti plus 1. How do we see that? Well, we just go back to our BSDE. We multiply this by the increment of the Brownian motion that we're interested in, and we take conditional expectation. The left-hand side, because it's adapted, will disappear. this part will remain in the product with the conditional expectation, and this part, by Ito's lemma, will just turn into the integral with respect to the Lebesgue measure of the process Z. That's how we get to this problem. Oh, that was funny. So, now what we can do is we put into our, we use the same orthogonality trick that we were using when we were looking at the process. You use the same orthogonality trick that we were using earlier on for the y process to just simply replace the loss function that was non-tractable or more difficult by a minimization. Yes, by a minimization with respect to the weight of the Brownian motion times the Lebesgue integral plus the terminal condition. Okay? So again, minimizing this is exactly equivalent to minimizing this. So the same phi will solve both problems. Okay? And now we have our first approximation, discrete time approximation of the loss function. So we've got this bit here, which was the loss in y, and this bit here, which was the loss in z. But because of these Lebesgue integrals, we still can't really turn this into a fully implementable thing. Okay? So, I'm just going to take a little bit of time to play a little with these conditional expectation formulations that we've made and form some equivalent continuous time representations for the solutions of our minimization problem. And those will prove useful when we're later on trying to build an explicit scheme, because the properties of the representations we use will later on have a very big impact on the performance of the algorithm. So these things will seem initially pointless, but in the long game will have a big effect. So the first representation is simply to apply the Tower law. And what we notice is here, we're integrating basically between time ti and capital T. Okay, so we're taking in the whole interval from today to the time where we mature, to the final time. If we just take the nested expectation, conditional expectation with respect to time ti plus 1, well, what we can see is we'll just be left with, if we just take the terminal condition and this Lebesgue integral from time ti plus 1 to capital T, that will be left with just this, the y at time ti plus 1. That's the definition of the BSDE. And what remains is this tiny portion of a Lebesgue integral with the driver. So this formulation is called the one-step scheme. So rather than looking in the conditional expectation at the outlook up to the end, up to the maturity, we just look one step ahead on our time grid. For Z, it's pretty much the same thing. We take the conditional, like we nest the conditional expectation at time ti plus 1 within our outer conditional expectation. It's just here rather the way we get. Yes, it's exactly the same thing as what we did before. We just have to notice that these guys are both measurable with respect to time ti plus 1. Therefore, we can just put the inner conditional expectation on this term and get exactly the same expression as we did before. Okay? So that's one-step scheme. We can also decompose our BSDE, our single BSDE, into a system of two BSDEs. So the first one, the little y and the little z, they don't have a term, a driver term. So they don't have this nonlinearity term in the time. And if we take a second BSD, this one doesn't have a driver, notice. It only has the nonlinearity in the time and Lebesgue term. But it depends on the solution of our first BSD, our linear BSD. And in fact, if we just add these two equations together, well, on the left-hand side, we'll have little y plus big Y. In the stochastic terms, we'll have little z plus big Z. And in the driver, we'll have little y plus big Y, little z plus big Z. We've just come back to our original equation. And this representation, although it may seem a little bit convoluted, given that we started with one equation and now we have two sets of equations to solve, actually it is quite beneficial simply for the reason that the functions that solve the first equation, well, they're solving a linear equation, and there are actually a lot more techniques that we already have to solve those kind of problems. So those can be usually quite efficiently solved. And the functions that solve the second equation, actually by omitting the terminal condition, we omit a lot of the non-smoothness properties or the explosive properties that that kind of drive the smoothness of the function y and z. That is to say, the functions solving this problem, this BSD here, actually they're much easier and more tangible to solve with numerical methods. So there is a real benefit to doing this. Okay, and the last problem I'm going to just introduce is just we add 0. Okay, what does it mean? Here, I've just gone from the first equation to the second equation. I've put in the stochastic term with respect to z, yeah, from time ti to capital T. Well, of course, in conditional expectation, that's 0. But the sum of all of this stuff, well, that was just the right-hand side of the BSDE. So it's equal to the left-hand side, and that's just YTI. And with respect to the filtration at time ti, YTI has no conditional variance. That's going to be very useful when we introduce the Monte Carlo schemes. Okay. And actually, we can do the same thing for the z. We just add now the z inside the term multiplied by the Brownian weight. We add the integral in z from time ti plus 1. We can also subtract off y at time ti. Why? Because this product with this has conditional expectation 0. And what we're left with, again, just playing with the BSDE form equation, is y at time ti minus y at time ti plus 1, sorry, minus y at time ti. Well, that's going to be small because usually the paths of y hold a 1/2 continuity. And this is just a Lebesgue integral over a very small period of time. So we're left with something that's very small. Okay? And these formulations are used in Monte Carlo regression BSD algorithms. And that's going to come later. Something much more challenging was an algorithm that was, well, a formulation that was turned into a numerical algorithm by Noëlla, Hu, and Song. So if you remember, we expressed the approximation of z as a projection. Okay? We had a conditional expectation involving integrals. Well, actually, we don't have to approximate z. We can use a representation in terms of Maillard derivatives. That is very well known in the BSD literature. And it basically tells you that you can express z as the Maillard derivative of y, which actually forms a linear BSD that, when you take the conditional expectation, leaves you a formulation that looks like this. Okay? And what they actually do in their paper is taking the linear, nonlinear, the linear BSD, which represents the Maillard derivative. Well, they notice that they can just perform a simple change of measure to introduce some weights, and they solve this equation numerically. We're not going to look at this further, but what we are going to, the reason I introduced it here is, in fact, this scheme here, it works only under quite restricted conditions, namely such where you have to have differentiable f and driver and differentiable terminal condition. or at least Malyavin differentiable. So what we can do is take this kind of clumsy formulation and apply the Malyavin integration by parts formula to get an expression for z in terms of a conditional expectation of the terminal condition and the driver, but multiplied by some Malyavin weights. And the Malyavin weights are now expressed as stochastic integrals involving the Malyavin derivative of x. Okay? So the downside is, okay, basically what we've done is we've shifted the regularity conditions away from the function phi and the function f, but we've put them onto the sigma and the b that we use to define our forward stochastic differential equation. So whilst we now can solve irregular payoffs or irregular terminal functions phi and more irregular functions f, we need to have more regularity and some at least stochastic ellipticity for the function, for the process x. Okay, so we're much more constrained on the x than we were before. The good news is, okay, unfortunately we also have to approximate this term, which involves this particularly this Malyavin derivative here, which is generally a matrix process, so it's quite tricky to compute, but in fact, for some more simple models like Brownian motion, geometric Brownian motion, we actually have the Malyavin weights in closed form. So that's quite useful. Okay. So so far what we've done is just rewrite the equation for y and z in different ways using the conditional expectation or some clever manipulation of stochastic calculus. What we can also do is we can approximate the functions phi and f in the backwards SDE. And what I mean by this is very simple idea. What I mean here is we can put some handy truncations inside the function f and phi of the parameters x, the parameters y, the parameter z. We can smooth the functions phi and f. In fact, we can apply any kind of change that makes the problem a little bit better behaved. There are then compute this sort of more friendly version of the equation. So we still have a backward stochastic equation, but now our phi and our f are slightly more kind to us. So we solve more stable kind of problems. And for some very key problems, people have proposed algorithms. The ones I want to note particularly are Jean-François, who's here, and Adrien Richoux, and Arnaud, and Lukáš, who are both here as well, if you want to speak to them. So Jean-François and Adrien, they solved the problem where the function f had a quadratic growth in the z term. So by some nice truncation techniques and some very sort of subtle truncation techniques that ensured convergence, they were able to approximate the quadratic BSDE. And Arnaud and Lukáš and Gonzalo, they solved the problem which could be polynomial in the y terms, which both of these formulations are important in sort of physical sciences like chemistry, statistical mechanics type problems. So, but I'm sorry guys, I'm not going to talk further about those problems. So they're very interesting and they have very successful papers in this area. Okay, so now I'm going to take one step further into getting our fully implementable formulation, and I'm going to discretize the Lebesgue integral. So my first guess for doing this is going to be pretty simple. I'm just going to discretize the Lebesgue integral on the time grid that I've already used to discretize my loss function. Okay? So it's just a first order approximation. And what I'm left with is a discrete time BSDE. Okay? So in fact, most of the terms will recognize them as they were before. So here we have a discretization of our Ito integral. Here we have the discretization of the Lebesgue integral. Terminal condition is the same as it was before. But what's appeared is this additional term L. So L is actually a martingale. And the reason it's necessary is because the discretized Brownian motion does not satisfy a martingale representation theorem. Okay? So in fact, for these equations to give you measurable solutions, it's not enough just to subtract a term in the discrete Ito integral with respect to the Brownian motion. You also have to take off a little bit more. And Kunito Watanabe tells us there's actually a unique triple Y, Z, and L. First of all, such that the product between W and L is a martingale. So this is a strong orthogonality property. And the unique solutions for Y and Z are given by these conditional expectations, in which we see instead of the Lebesgue integrals that we saw earlier, what we see appearing is the discretized sums of the Lebesgues. So these are actually exact discrete time analogs of the conditional expectation formula we had for Y. And this one is an analog for the conditional expectation expression we had for Z. This one here. Okay? So in a way, we're back to where we started. We've just discretized everything, and we're one step closer to having a fully implementable scheme. Yes, who is it? Yes.
I just want to check what are the variants of the random variable that is inside of the explication of C.
This one?
Yes, particularly the first one, the second line.
This one? This is a very good question. So the what would be the variance of this one?
The second term, I think,
no, the second term is worse.
Delta WY divided by delta I is a problem, right?
It is, yes. So this is actually a critical point, and it will come up a bit later when we're implementing the term. But so I can raise it. Typically, this term here, the dividing by the time step, is a problem. Why? Because in expectation, if we just assume everything else is nice and bounded, the expectation of the variance of this term here will be of the order 1 over the square root, 1 over delta. Okay? So that's going to be a problem that we will treat using variance reduction techniques. Okay. So now what are we going to do? We're going to update our loss functions. So remember now what we're trying to do instead of finding minimizing functions against Lebesgue integrals, we're just going to try and find minimizing functions with respect to these discrete sums. Okay? So we're still not at the stage where we have a tractable algorithm, simply for the reason that the Y's and Z's were computed with conditional expectations. And usually you do not have analytic formulae for conditional expectations. Okay? So we're going to get around that by introducing least squares method in a few slides from now. So, and Raoul, this is kind of coming back to your question slightly. Just like for the continuous time setting, we can play around with our conditional expectation formulations using, in the first case, the Tower property to have a discrete time version of our one-step scheme from earlier, or just adding 0 to get back to have this analog of So this first set of equations here, if you recall, we already saw it, its continuous time version earlier. And the second set of equations, we already also saw their continuous time version. So this was the continuous time version for y. And for z, this was the continuous time version. So again, we subtract y and subtract the Lebesgue integral. Sorry, the stochastic integral. Okay, so here we see we subtract y and we subtract the stochastic integral. I keep trying to edit my slides. Okay, and again, this actually, for the same reason that this thing here has lower variance, in the continuous time setting, this will have much lower variance in the discrete time setting as well. This is one way that you get around this variance problem caused by dividing by delta. Okay, but that's coming up. So finally, what we can show at this stage is that this, our first approximation, discrete time approximation, will converge to the continuous time equation as the number of time points that we put in our time grid goes to infinity. But we need some conditions, and they're fairly loose conditions. We insist that the terminal function is Holder continuous, and we insist that the function f is bounded when y and z are 0, with a bound that can explode, but not too quickly, as we approach the terminal time t. And we also want it to be Lipschitz continuous, with a Lipschitz constant that depends on time, which can explode again as we approach the maturity. We also require quite heavy conditions on the coefficients of the forward process, so we require some differentiability and some ellipticity for the sigma. But it means that we can treat quite irregular payoff functions. And what we find is, depending on the regularity of the payoff function and the size of these explosive terms, our convergence will either be order 1, so this is the convergence of the square loss, will either be order 1 if we're regular enough and if we're not exploding not too quickly, or it will be converging at some error that's less than that and dependent on the, so it depends here on the different coefficients that we've put in. Okay, so if we have a slightly friendlier payoff, so just Lipschitz continuous, we can actually relax completely our conditions on the coefficients of the forwards process. So we just need them to be Lipschitz with linear growth. And then we can actually show, so Tsang showed that this has convergence order 1, if we just take a uniform time grid. And Gobet and Labarre show further in that if the payoff is even smooth, then the convergence rate increases to order 2. Okay. But we have to be much smoother in phi compared to previously. Some alternatives that have been proposed, one recently due to Gilles Pagès and Sagna, who studied this discretization scheme, where now we see, rather than having the conditional expectation outside the driver, we put it inside on y. So they studied this problem in the context of quantization algorithms, but I thought it was of interest, and this paper is certainly very interesting, so I thought I would flag that. And then there's also an implicit version of this algorithm, which is theoretically tractable, so the solution to this does exist, where, as you can see, we have y, rather than putting yi plus 1 inside the driver, we just put yi, which means that both the left and right-hand side depend on yi, so it's implicit. Okay? But the importance of this scheme is quite large. In fact, Chassagneux and Richoux showed in another paper that this scheme is numerically far more stable than the explicit type of scheme. So they have a very nice paper on stability properties of discretizations of BSDs. And just to mention, if you do want to apply an implicit scheme, the way you can do it is by a Picard stepping type scheme. So we have a one-step version, which was developed by Gobet, Lemort, and Warin, and a multi-step forward version created by Bender and Denk. So basically what you do is you just check in any initial guess for y and z, so it could be 0. And then you sequentially solve for y and z by plugging in the value of y and z that you already computed in your last iteration and working repeatedly backwards over the whole time grid. So this is just a Picard type scheme. You do it either do it one step at a time, or you do it all the steps in one go. And I'm just going to end this section with higher order discretization schemes. So all the schemes that we've looked up to right now have just been first order discretizations of the Lebesgue term. So we had the Lebesgue integral, we performed the first order discretization, and we got these convergence rates of order 1, order 2, depending on the smoothness of the payoff. So Jean-François, together with Dan Krishan, who was here earlier this week, developed a so-called Runge-Cutter scheme, where you have to make not only approximations at the points of your time grid, but for each time step you make additional, like, inner approximations. So between any two time points, you make more approximations, like small time approximations of y and z, in order to permit you to have just a finer quadrature on your Lebesgue term grid. So all of these parameters have been painstakingly worked out in the paper by Jean-François and Dan. So I really recommend you have a look at it if you are interested in these kind of higher order schemes. And they're actually able to attain convergence rates up to order 6. Okay? Depending on how many stages that you introduce into your approximation. We can also discretize our Malievan representation. So this is something I did together with Emmanuel. So if you record the Malievan representation in terms of the integration by parts formula, we had it in continuous time here. So now what we're going to simply do is discretize this Ito integral here, discretize this Lebesgue integral here, and we wind up with our discrete time scheme for z here, where now we have discretized versions of the Malievan weights. The y approximation doesn't change. Okay? Of course, now we have to change our loss function for the z to include the Malievan weight terms. But we also, I also showed in a paper that this scheme converges to the continuous time BSDE under the same conditions as I had earlier. So I can have phi being a Holder continuous, I can have explosive growth and explosive Lipschitz constants, and I achieve the same convergence rates as I did for the previous just simple scheme. The downside is, well, first of all, I can't get rid of the constraints on the coefficients of the forward process, and yes, at least I don't know that it's been possible to prove that the convergence rate is better if you have smooth payoff rather than just Lipschitz payoff. So it has certainly some constraints, but the convergence rates are the same. So finally, we come to least squares regression. So I'm going to go back to a more general setting. So like I'm going to dissociate us from the setting of the BSDE for a moment, just to introduce some key results on least squares regression that we're going, or Monte Carlo least squares regression that we're going to use going forwards. So the first thing that we're going to do is we're going to introduce this functional S, which when we inject some process into it, yeah, we're just going to sample the trajectory of that process at the points of the time grid. Okay? Then what we're going to do, this functional is going to be random, and what we're going to do in a second is we're just going to inject the paths of the process x. Okay? But this can be any functional for the moment. Just so you know where this is going, in a few seconds I'm going to replace S basically by, yes, I'm going to replace S by this term here. Sorry, this is for the Bender-Denk scheme, but it's easy enough. Okay? So then I have a loss function, which is given by, basically what I want to do is I want to find the function phi, which is just a function of x, which minimizes this least squares error here. And in fact, we know what it is. It's just the conditional expectation of s, given that x is equal to x. The function, the process xt is equal to little x at time t. Okay? So the problem with this is, so this is a good setup for a numerical algorithm because we can now, since we now have a minimization problem, we can start thinking about gradient descent methods or all of our kind of theoretical minimization kind of techniques. The problem is usually we can't compute this expectation analytically. Okay? So for any kind of search policy that we want to develop, any kind of descent method algorithm that we want to develop, this won't work just because we can't compute it. So one idea might be, okay, let's just replace the law with the empirical measure. So we can sample from the process x, we can sample from the functional s. Why not just replace the expectation with the empirical measure? Okay, now we have our usual Monte Carlo setup. Of course, the problem here is the set of functions over which we're searching is infinite dimensional. So that's again completely inappropriate for a search policy, for a search algorithm. So we have to do an approximation in two steps. We have to approximate the function space, and we have to approximate the measure. So the first step is to take a space of functions on which we hypothesize that our solution is going to live. Okay? So we call this a hypothesis space, of course, and it's just a subset of the set of order functions that we can choose. Okay? And it's going to be finite dimensional. So now, rather than now rather than searching over all of A, we're going to search only over K. So this is going to be a further approximation. And the interesting thing is that the error in approximating on K rather than on A is basically going to be the minimum error of approximating phi star, that's the conditional expectation solution, on the set K. Okay? So the further away, so that's basically what this tells us, that this selection of this space is crucial, obviously, because the further away we are, the worse our selection of the space, the bigger the bias in our final approximation is going to be. Okay, so the second step, we are going to approximate, just like before, we're going to approximate the law by the empirical norm and approximate now our loss function rather than with the expectation, just the mean. Okay, the mean loss over our samples. rather than the expected loss. Okay? So now, finally, what we can do is if I just simplify my notation, so what I'm going to do is I'm going to write a matrix X whose rows are going to be the samples of the process X, or at time ti, and whose columns are going to be the basis, the values of the different basis functions that I've used to represent my linear approximation space. Yeah? And Y is just going to be a vector of all the samples of the functional S along the paths of X. And now I can just write my loss function, or my minimization problem, as the minimization over all of the the RK valued numbers beta, such that X times beta minus Y is minimal in the L2 norm. Okay? And this is a fully tractable, solvable problem, otherwise known as least squares regression. Okay, so is it too early? I'm going to go through how we actually estimate the error of this approximation. And after that, we're going to take a break, because it's quite heavy. So basically, now that we've set up now that we can actually compute our approximation for the optimal function phi, what we're interested in is what is the square difference between the true value of phi star and the one that we've calculated. Okay? The main problem we have in comparing these two values is, of course, this one is generated from samples, whereas this one is generated from a law. Okay, so those two things are, this one is especially difficult to understand in terms of the law. On the other hand, we know a hell of a lot about this function in the empirical norm. So the first thing we're going to do is we're just going to add and subtract inside this outer expectation. We're just going to add and subtract the L2 error, that's the L2 error over all of the samples, between the function phi star, the optimal function, and the function that we've computed. Okay? I've just put the dot in here where I've usually been putting the notation for the sample number to indicate that the L2 norm is being taken over all of the samples. Okay? And so what this term here is, it's actually a term of divergence between the difference in the two phis under the true law and the difference in the two phis under the empirical law. And you'll notice there's this very important feature here, is that I've subtracted 2 times the empirical difference, not 1 times the empirical difference. So what I'm looking at it is a true divergence between the two laws, and I'm going to capture that even further by, first of all, only looking at the positive difference between these two terms. Yeah? So that's what this plus is around here. And to truly estimate this term, what I unfortunately additionally have to do is, rather than looking at the perfect function, phi star, that I've computed from the least squares regression, I'm going to have to take the supremum over all of the possible functions phi in my linear space. I've snuck something in that maybe some of you have noticed. I've made the assumption that the optimal solution is bounded. In fact, in the BSDE setting, it's not very difficult to force this kind of condition by truncating the payoff function. And the error you introduce is very low by doing that. Anyway, what we're left with is 2 terms to approximate. First one is this divergence term. The second one is just an error in the L2 norm. So, in fact, the first term, the error for the first term, comes from a very profound theory. It's not just our paper that's covered this problem. It comes back to 90s, 80s, and before. This is just one reference at the tail end of this theory rather than at the forefront, I would say. So what this, in fact, these, to estimate this, I'm not going to go into the details of this because it is truly horribly technical. It involves going very deep inside the structure of the function space that you're trying to approximate and looking at things like the Vapnik-Chervonenkis dimension. And it basically, the problem is because these functional spaces are so complicated, you end up having to be extremely conservative when you're making these estimates. So not only are they very difficult to obtain, but they're extremely conservative. So this number here, as you can see, is quite astounding. We're multiplying by 2,000. You wouldn't usually like to see that in your error estimates. But the important thing that we get from this is actually as we increase the number of samples, these terms will converge to 0. Okay? So this is a proof in principle that we're going in the right direction. And two things to note, actually, this is the error here is proportional to the number of basis functions and inversely proportional to the number of samples. Okay, plus a log term in the number of samples, but the downside of it is also, if you notice on the right-hand side here, we don't see anything about the variance of the functional S. So the thing we've projected can have as little, like a very small amount of variance, but a large just deterministic variability. So it can cover a large range of values, but have very little variance. And that wouldn't seemingly improve this estimate. Now that suggests that BSD algorithms involving least squares regressions can't benefit from variance reduction techniques, which doesn't really feel right, and in fact isn't right. So this, unfortunately though, in the very general setting, we have to work with these kind of estimates, or at least I haven't been able to improve them, or nor has anybody I know. Yes?
I'm getting lost with the notation, so just to be sure.
Yeah.
Here we are taking into account the Monte Carlo.
Yes. So this is the Monte Carlo generated norm.
So can you give me an intuition of why it converges like 1 over m rather than 1 over square root of m?
Because of this 2 term. And unfortunately, no, I can't give you an intuition. If this was 1, it would be 1 over square root of m. But because we're taking the positive part and we're pushing it far enough away, of course, this term is just becoming, the bigger the multiplier here, the more likely this thing is going to be 0. So the smaller we're making the value. The point is, a factor of 2 is not really a big deal for us. Okay, so we're actually interested in estimating this term. We don't really care about this factor of 2. We just want to make this thing go away. Okay. Coming to the other term. So this was the second term now. So we've dealt with this guy here. Now we're going to deal with this guy. So this is the expectation of the least of the empirical error. Basically, we just have to make a few. We have to introduce a few intermediary terms. So in the first step, what I'm going to do is simply, if you recall, I had the truncation to make sure that my approximation was in the bounds minus L and L, so the same bounds as my true solution phi. So that just gives a simple inequality there. In the second term, I'm just going to add and subtract this p times beta hat, and the beta hat is the minimizer of the function phi star, that's our optimal function, in the linear space of approximation under the empirical measure we used for our least squares regression. Yeah? So here we have used the same samples as we used for beta star. We've used the same basis functions, but rather than projecting S, we've projected the optimal solution. Yeah? So because this is a projection in L2, actually Pythagoras gives us an equality between this difference here and the sum of these two differences. Yeah? Where here we have the difference between phi star and its projection in the empirical norm, and here we have the difference between the two projections, one of phi star and one of S. Okay? And in fact, this first term is exactly is bounded above by the bias. So this is exactly the term which is the minimum error that you can make on phi star by approximating in the basis. Yeah? So it's the second term that's going to give us a little bit of trouble and that we need to deal with. Okay, least squares has this very nice property that you can represent its solution explicitly through what's called the normal equations. So the minimizer beta star of this least squares problem, x beta minus y, can be expressed as x transposed x times beta star is equal to x transposed y. We'll come back to the normal equations in the second part of the talk. But basically, to estimate these terms here, we're just going to first of all ignore the expectation and just work on the inner norm, yeah, the inner L2 error. And in fact, I can assume without loss of generality that the basis functions are orthonormal in L2, in the empirical L2 norm. Okay? The reason I can do that is I can apply some pivoting simply without actually changing the norm to make sure that the basis functions are the same. Sorry, the L2 distance is the same, but just having changed the basis functions. So I can perform rotations on my basis of vectors, basically. So basically what it means is this L2 error is exactly equal to just the L2 difference between the two sets of coefficients. So now I plug in the exact formula that I have for beta star and beta star hat that I get from the normal equations. I do some expansions basically because I have a square here, so I have to do some expansion that gives me quite a nasty long sum here. So we're summing over two sets of samples and over all of the basis functions. But this is the key thing to notice. We know that phi star is the conditional expectation of S. Yeah? That was the very first thing we said. So in fact, what we have here, and because all of our samples are independent, what we have here is the difference between S and phi star multiplied by the difference on S and phi star, but for a different sample. Right? So if I take the conditional expectation now with respect to the samples of x at time ti over all of the possible samples that I've taken, what we see happening is, okay, well, these guys are going to be measurable, so it's just the conditional expectation of this product here that's left over. And for all of the terms where M1 isn't equal to M2, we use the independence and the fact that this is just the conditional expectation of this to show that the terms, the non-diagonal terms that we get here are 0 under this conditional expectation. So that's exactly what we do. And of course, the diagonal terms are all equal to the variance, right? Because it's It's S minus its expectation squared. That's variance. So what we're left with, in fact, is when we take the expectation, take the conditional expectation inside, what we're left with is an upper bound given by the, oh sorry, there's two Ks, given by the maximum conditional variance of S, given that xti is equal to x. The K appears basically because all that's left over is the product of the product of the orthonormal basis functions and divided by m. Okay. So now, actually, this is very similar to the error we had just a few slides earlier. So this was the error that we had from concentration of measure. It was, again, proportional to k, inversely proportional to m, except now what we see appearing in this error term is also the variance. So this term is sensitive to the variance of S, whereas the previous term was not. And before we stop for a break of 5 minutes, I'm just going to say that actually we did have some result with Emmanuel, where we managed to prove that for certain classes of basis functions, particularly the piecewise constant basis functions, taken on disjoint subsets, disjoint continuous subsets, not continuous, sorry, but disjoint complete subsets of your space Rd. What we could do is basically taking advantage of the very specific structure of these basis functions, we could compute the square error between the optimal solution and the least squares computed solution and bound it above in terms of, again, the bias terms, but now terms involving the variance only. So we don't have any terms which are non-sensitive to the variance anymore. Okay? But this was for this very specific class of basis functions, and I don't know any other results which try to extend this except for, I think, some sparse grids and things like this. So unfortunately, if anybody does know something, please let me know, because it would be a very, well, I would find it an interesting result. So this is the very general setting. I'll just show you a picture for, excitement purposes. When we come back, we're going to go back to the BSDEs and apply the least squares regression to the BSDEs and fully and complete our work by fully introducing some fully implementable algorithms. So yeah, 5 minutes. So we just went through quite a abstract recount of the least squares regression method. What we're going to do now is we're just going to go back and put it into the context of BSDEs again. So in the last few slides, what we were trying to do is work out the conditional expectation of a functional S. Okay? Now we're going to give form to that functional, and it's going to be the thing that we want to compute the conditional expectation of in order to get our discrete BSD solution. Yeah? And the way to think of it so far, from what we've been doing, is say we want to compute our conditional expectation at time 0, or our expectation at time 0. What we do is we simulate a bunch of paths of the process x, and at the time points of our interval, of our time grid, we evaluate the driver. So it means that we evaluate x. We also evaluate the functions y and z, which we've already computed in previous steps of our time grid, of our algorithm. Now, this is the idealized picture. Why? Because it assumes here we have such an accurate approximation of the y and the z in the periods that we've already done that it's pretty much touching the true solution. The reality tends to be or could be very different. So if we were just using piecewise constant approximations, well, we see here in the light green, or maybe we don't see it, but anyway, I promise you there's a light green line there, that our approximation might be quite far away from the true solution. So the problem we're getting is that at each time point where we compute a new conditional expectation, we're carrying all of the errors that we've approximated, that we've incurred in the previous steps of our algorithm. Okay? So, briefly to say what we're doing, we know the solution of y at the end. We then go to the penultimate time point, approximate our conditional expectation at the penultimate time point, then use the approximation and the terminal value to approximate the next conditional expectation, and we go back and back and back. Okay. But at each additional level of approximation, we're going to introduce all of the error that we've already incurred in the previous steps. So I'm sorry for this slide, it's very dense, but essentially we saw this already. Okay? So in the abstract setting for the least squares regression, what we introduced was this beta hat star fictional coefficient. And it was the one which optimized the it was the least square minimizer when we project phi star using our empirical least squares norm. Now that was, I think that, no, so this should be beta tilde. We've introduced a second, in this second inequality here, we've introduced a second coefficient, beta tilde. So sorry, that should be beta tilde there. And this here now is the minimizer in the least squares norm, in the empirical L2 norm, of the conditional expectation of our SM. So SM was this functional here. Okay? So we take the conditional expectation of this functional along with all of the approximated all of the approximated y and z terms, and it leads to now two new terms to work out. Here we have the difference between beta hat and beta tilde, and here we have beta hat and beta star. So this guy we've already dealt with, this guy we've already dealt with. It just remains for us to deal with this guy here. So this was the bias, this gave us our statistical error terms. What about these guys here? Well, these guys are actually very nice. And the reason they're very nice is this very simple property of Pythagoras' theorem, which says that, well, these two coefficients are the least squares optimizers in the L2 norm when we project y and the conditional expectation of S. Therefore, the distance between these 2 points has to be less than the distance between y and the conditional expectation of S. But, in fact, what we can say about this conditional expectation here is that it is, in fact, the solution of a discrete time Brownian BSDE, which has exactly the same terminal value as y, but whose driver is just a function of t and x given by the conditional expectation of x and the functions y, m, and z, m. So basically what we're doing is we're fixing the y and the z in the second BSDE. So this is basically the difference in the least squares expectation, in square expectation, between the original discrete BSD and this new fake BSD that we've just constructed. And in fact, what we can do is we can estimate this error using a priori bounds on discrete BSDs. And I'm not going to go much further into it, but what I will tell you is that this basically just gives us error terms containing the difference between the y's and the z's, the true y's and the empirical y's, and the true z's and the empirical z's, between ti all the way up to the terminal time capital T. So this introduces these propagation of error terms that we spoke about before. So these terms, the a priori estimates on this capture perfectly the error that we have introduced by approximating y and z multiple steps before. And the nice thing is all those errors are actually going to be weighted by the time steps. Okay, so basically you end up summing up over all of the future time points the error between the y and the z, but you weight it you average it over the time, in fact. So each contribution is quite small. If we look at this one-step scheme, so this was all this multi-step scheme. The one-step scheme, by contrast, this is where we only look one step into the future. Yeah? When we get to this step of the approximation, so now we're using S hat instead of S hat M instead of SM, what we see is rather than projecting rather than taking the conditional expectation of a fixed functional of what this fixed this doesn't move. So rather than taking the conditional expectation of all of the future values of phi and the driver, we have this term here that's just plonked itself in. Now, this doesn't form a BSDE anymore. So this just, you don't have a dynamical programming setup if you just use this, because basically this is computed by least squares regression rather than by conditional expectation, and least squares regression doesn't have the tower property. So whereas previously, when we moved between the one-step and the multi-step scheme with the conditional expectation, there wasn't any difference. Now, because we have the least squares regression operator, they're two completely different things. So we lose this propagation of error. We end up having to do Gronwall. All of the errors will add up and we lose this nice time averaging property. Okay, so that's all I want to say about that at this stage. The only other thing I'll say is for the Maliovan weight scheme here, essentially, although the techniques for all of these proofs are quite different, so the technicalities are quite different, the same kind of methodology can be applied to get the same kind of error estimates. So actually the way that we go about proving the error for the least squares version of the Maliovan weight scheme is exactly the same. The benefit of the Maliovan weight scheme, in fact, is the weights that you use in the Z part do explode as you get close to the terminal value, but in fact the further away you are from the terminal value, you don't get this 1 over delta effect anymore. It's something like 1 over the square root of the time to maturity, and that's much lower variance. So that's why we introduced that scheme. Okay, how to solve least squares regression on a more technical point. There are two methods that people usually look at. So we earlier introduced this normal equations. Okay, so what we said is that we can explicitly give any solution minimizing beta in terms of this linear equation here. Now, what we can do is we take this matrix product here, take its pseudo inverse, yeah, and that gives us A beta star being the minimizer with the smallest L2 norm, is given by the pseudo inverse of x transposed x times y. Okay, so that's the solution to that. The problem with that solution is to do with numerical stability. So when you look at numerical linear algebra, a term that you're very concerned with is called the condition number. So the condition number is basically it's basically the quotient between the maximum non-zero singular value divided by the minimum non-zero singular value of your matrix system. So you do a singular value decomposition, you find what's the maximum and the minimum non-zero singular values, and you divide them. And the influence that has is basically on how stable is this product. So in a real machine, you don't get mathematical solutions. You get small errors because your computer can only represent a number up to a finite number of decimal places. So what you end up inputting is not y, but y plus some small term epsilon. And when you want to measure what is the relative error of the solution y plus epsilon versus just y, this is basically proportional to this conditioning number. So if this is very big, this error will be very big. And the problem with the normal equations is actually, since you have a matrix X transpose times X, the condition number of the pseudo-inverse is equal to the square of the condition number of X. So if the condition number of X is already bad, this is going to be much worse. Okay, so if the condition number of X is large, X squared is much larger. So what people tend to do is QR factorization. So what QR factorization basically is it's a recognition that the L2 L2 distances are not changed by multiplication of an orthogonal matrix. Okay? So if I take any orthogonal matrix, multiply my vector difference by that orthogonal matrix, its L2 norm is exactly the same as if I'd never used the orthogonal matrix. Now, the QR factorization is simply it's actually every matrix has a unique representation as a product of an orthogonal matrix and an upper right continuous matrix. Yeah? And now, if I just use this property here, if I multiply everything by the transpose of Q, starting here, I multiply everything by the transpose of Q. Basically, my Q in X is going to vanish, and I'm going to be left with the solution solving the least squares problem between R1 times beta minus Q transpose times Y. Now, R1 has full rank and is upper diagonal. This is basically the solution of a simple solution of a linear system. So this is completely trivial. And the condition number, like the condition number of this problem, is now reduced by the square root of the previous one. So this is what people will usually do. So I just want to talk a little bit about this problem of generalizing or generalization, or how to choose the hypothesis space, how to choose the basis functions. So what we actually care about, so we've taken our sample, we've computed some coefficients. What we want to know is that really a good approximation of the least squares error? Okay? We've just taken one sample. And there's something that's called the underfitting overfitting problem. So basically what it tells you is, as we look at the number of bases, let's just fix a set of data. And as we increase the number of basis functions that we use, basically what tends to happen is if we have too few basis functions, we're going to have a big error because basically we just don't have enough basis functions to approximate the true solution. However, once we start injecting too many basis functions, if we don't increase the number of samples that we use, what tends to happen is the basis functions will start fitting themselves to the data too well. So they'll become too specifically fitted to the set of data that we generated to compute the coefficients. So you can, and what you can do to observe this is basically you have your set of data that you've used to compute coefficients. You draw some IID data, so some independent data, and you compute the least squares error on the set of IID data. So on one set of data, you compute the coefficients, and on the second set of data, you compute what is the least squares error between what you tried to project and what you got. And this is actually a typical plot of what you'll get. So this is the underfitting, overfitting phenomena. But the cool thing about doing that is, since you have a separate set of data on which you're actually evaluating how good is your fit to a new set of data, the set of data that you actually use to compute your coefficients, you're not married anymore to using least squares regression. You can actually put anything you like in there, because on the second set of data, you're using the least squares error. Okay? So what you can start doing is doing something called regularization. So you can add a penalty function that tells you, okay, I don't believe that my coefficients are going to be very big. So you just add mu times the L1 of the coefficients and minimize that along with the least squares error. And it's quite interesting. The orange line here, this is the least squares error that I computed for a problem. This is just this is a mind experiment, really. So if I computed using this penalty term, I got this blue line in terms of the error. If I didn't use the penalty term, what I ended up getting is this diverging error on the least squares. And if you look at actually, because I could compute explicitly what the true coefficients were for the real solution, you can see why this is happening. Basically, when I penalized, my coefficients actually converged to the true coefficients. Whereas when I didn't penalize, they fitted themselves to the data however they wanted. Some tricks for BSDEs. So now this is specifically some tricks that work for applying regression to BSDEs. So the method that we've introduced is actually very general. Okay? The problem is, so it can treat any kind of regularity. It can treat higher dimension or problems. Typically, we want to use it to solve problems which have a very high dimension in X. So the D dimension is quite high. And there we're basically constrained by memory in our computer and also computational time. Okay, we don't want to wait for 1 month to get results. So the first trick we can do is re-simulate the trajectories for X for every single computation that we make. So if I go back to this picture, what I see is that as I simulate forwards, I already have all of these solutions to Y and Z. I want to form this sum. So as I go forwards, I just compute what I need to using the trajectories that I've computed so far, and then I throw away the X terms. Then I keep going forwards, do it again here, do it again here. If I re-simulate every time, I don't have to store all of the simulations for the X's. Okay, so that saves me a little bit on computational space. It takes more time, but the problems become more tractable. The second thing is use variance reduction. So we've seen already that actually we do capture the effect of variance reduction inside the least squares regression. And what I'm particularly thinking of is this term where we subtract the stochastic terms. And also, in fact, the Malia-Van Weyt scheme, because like we said, it has a lower variance than the multi-step forward scheme. You can reduce the number of time points you use by using a higher order scheme. Oh, sorry about that. So that's a la Chassagne-Cuisan. And if you actually don't care about having a solution globally over the space, if you only care about the solution at one point in time, well, actually, and you don't mind waiting a bit longer because your variance is a bit higher, you should actually use the one-step scheme. So in the one-step scheme, remember, all we need is y one step ahead in the future. We don't need all of the y's in the future. So once we've computed a set of coefficients, we use them for the next iteration of our algorithm, and then we can throw them away. And in high dimension, the coefficient memory consumption is really high. And finally, we're going to use a method called uses to, we're going to use a method called uses, which I'm going to introduce in just a few slides in order to improve the stability and leverage high-performance computing techniques. Just a very simple example. This is basically the example I'm going to use in all of the numerics that I show down below. Together with my PhD supervisor, Dirk Becher, we developed a variance reduction scheme and analyzed it. It was basically a combination of this system of splitting into two BSDEs and this variance reduction technique here. And yes, this is actually just a table of the mean square errors. And what we saw actually is, particularly for the z's, the mean square errors were significantly lower when we used this scheme. Oh, hate you. Anyway, the last thing I'm going to show is very, very fast, because I have to finish soon. So one thing that we can observe is that wouldn't it be great if we can stratify our sampling? Okay? What do I mean? If we look at this very simple set of basis functions that we've used, this is like piecewise constant. The problem we see is all of these trajectories that we've simulated are random, right? Obviously. So the number of particles that land in each cell is going to also be random. The stability of the approximation in each of these cells is going to depend on how many particles land in that cell. Yeah? So we need as many particles landing in each cell as possible. Now, this is obviously not going to be very stable if we are simulating from a fixed point all the way forwards in time. But if we knew what the distribution of x was at any of these time points, that would be great, because we could actually simulate by stratified simulation directly into each of these cells. So we could actually start the trajectories in the blocks where we needed them to be. Also, if we knew that we had some nice orthogonal bases, then we could make sure that we have a low condition number. The problem is, of course, that the distribution of xi is rarely explicit. So together with Emmanuel, and some other co-authors who are here, we developed a generic method to do the stratified simulation. And it's basically based on the idea that, well, y and z, they're computed by conditional expectation. So if x is a Markov process, in fact, the functions y are uniquely determined by the transition function of x. They do not care about what the law of x is at time ti, only what its transition density is going forwards. So actually we can choose any random variable we want in order to initialize our trajectories. That means we can do stratified sampling in any way we want. The problem is the propagation of error. So if we actually want to prove that a system like this converges, we need to have some consistency in the laws of the paths of x. And I'll show you what that consistency is on the next slide. So there was a condition we found works very well. So if we can choose any law with density p, which satisfies this uniform sub-exponential sandwiching property. It basically means the convolution of the law with a Gaussian has to be bounded by itself, from above and from below. And the consistency I mean is that the consistency in the law that this brings is that basically the expectation squared of x at any point in the future under any square integrable function phi is bounded from above and below, or is equivalent to the expectation, the square expectation of the same function of x at time I, that is today. So that means basically this, the square expectation, the law is going forwards in time is somehow fixed between two bounds and proportional to that same square norm today. Okay? So we've effectively sandwiched the square law of the process of x. Okay? And this is exactly what we need to prove convergence. So we did this with Emmanuel, Jose, and Carlos Vasquez. And it turned out that even though this seems quite complicated, it's satisfied by very standard distributions like the Laplace distribution and the logistic distribution. Yeah? So actually, it's very easy to do stratified simulation. This is just to show you what happens. So if we start with a Laplace distribution, so if we simulate our points from a Laplace distribution, this is what the distribution of the marginals looks like going forwards in time up to time 1. So it's actually almost stationary. So that's basically what the sandwiching property is doing. So we actually implemented this algorithm. We implemented this in our least squares regression algorithms and did it in parallel, actually. So we simulated parallelly. We solved the BSD in each of the cells of the space discretization in parallel. On the one hand, over a multi-core CPU. On the other hand, over a GPU type processor. We only needed 6 gigabytes. Basically, so this here we showed some results in dimension 6 already. So this is where the basis was simply piecewise constant. Basically, we found the GPU performed very well on this because piecewise constant bases are extremely easy to solve with very elementary operations. And then we used also affine basis functions, piecewise affine basis functions, to enable us to go to much higher dimensions. So we actually went up to dimension 20. Now, because we were fitting affine functions, basically the GPU still outperformed the CPU, but it wasn't so profound. But the interesting thing here was we could go to such high dimensions because we were able to manipulate the stratification in a very memory optimal way. So we could do all of these computations using only 6 gigabytes of RAM up to dimension 19. So I think that was good. One last variance reduction scheme that comes out of this uses type concept is we had this importance sampling idea with Emmanuel. So the idea here is I'm just going to represent X very generally here. So what we've been looking at is these conditional expectations. We're back in the continuous time framework. So we express Y as a conditional expectation. Now, if we change the measure, like if we change to an equivalent measure, we know basically that this conditional expectation will be the same so long as we change the drift term for the process X and we multiply everything by some weights. Yeah? So the weights are on the next slide. And what we found with Emmanuel is that actually we could minimize the variance, the conditional variance of the terms that we wanted to approximate by insisting that our changed drift was simply the drift plus the original drift plus sigma times z divided by y. Okay? This would actually reduce the variance of this to 0. I'll show you that on the next slide. So the only problem with that is, of course, we simulate x going forwards in time. Now what we're saying is to simulate x, we need a drift that depends on z and y. Well, z and y are computed backwards in time. So we're actually left with a big gap in the time interval where we wouldn't be able to simulate from time 0. So we use this uses idea to simulate rather than from time 0, we went to simulate directly at the time point we wanted to compute the regression. And it's exactly the same uses technique that we had in the last slide. And that completely avoids this gap in the simulation between time 0 and the time you want to regress at. Okay? So this is the justification for why the algorithm works in continuous time. This just, so essentially what we do is we look at, we apply Ito to the term inside the conditional expectation here. We do a little bit of work and find at the end that we're just left with y at time t plus an Ito integral that depends on the difference between, oh, this has run out of battery, that depends on the difference between z and y times h, h being the change of drift. So if h is just equal to z divided by y, this stochastic integral here, I'm going to use my mouse, this stochastic integral is going to go to 0. So that explains why we have the z over y appearing. Okay? And we can turn this into a fully implementable algorithm using uses. And we did this, we computed z basically using the Mallier-Van Weights type approximation. No, I've only got one more slide, so it won't matter. The downsides of this scheme were, in fact, we weren't able to effectively leverage some kind of change of variable scheme for the z part, so the z didn't have any variance reduction applied to it. And we also couldn't, in our error analysis, we couldn't so far include z into the driver because the lack of variance reduction on z would then propagate onto the y, which would mean everything would break. But still, when we implemented it, what we got is some very nice evidence of significant variance reduction. So the red histogram is just some, this is the just a plot of computations using several, like 100 runs of the importance sampling algorithm, whereas the blue histogram doesn't use the importance sampling. And the reason there are two graphs is on the right, we did it again, except we used a sloppier computation of the z just to demonstrate how important getting an accurate approximation of the z is. Okay? So those were the methods I wanted to show. With that, I want to thank you all for your attention and thank the organizers again for having invited me. And yeah, take your questions.
Okay, thank you for this nice lecture on regression techniques for BSDEs. Does any one of you have a question? Yes.
Thank you. So, concerning the part where the slide where you said trick for BSDEs, so you talked about applying the higher order methods.
Hello? Ah, sorry. Okay, sorry, please again. Yeah?
Yeah, so you talked about applying higher order methods.
Yeah.
So I'm not sure, but for higher order methods, you need more regularity on the coefficients, no?
You do need more regularity.
So, on the other hand, the regularity should be data and the problem, no? So if you have a problem with Lipschitz coefficients, how you can get to the higher order methods? So
the point is, even if you have a very smooth problem, even if you have very smooth coefficients, you can't take advantage of that smoothness using only a first order approximation of the Lebesgue integral. That's why you have to implement this higher order kind of quadrature of the Lebesgue integral in order to get the higher order convergence rates. Does that answer the question? Or?
Yeah, but the initial problem is, let's say, with Lipschitz coefficient, Lipschitz terminal condition, and Lipschitz driver. So,
okay.
Is it possible to go to? So, is it applicable in this context? Or?
I think you have to ask Jean-François that question directly.
Okay, I will do this evening. Thank you.
Is there another question? Well, if not, thank you again, Plamen.
Thank you.